So can you see the slide?
Yes,
Yes,
sir.
sir.
Okay, today I shall discuss short channel effects, particularly in connection with MOSFETs. The short channel effects actually occur when a gate field loses its control over the transport of channel carriers. When the source and drain are brought to close proximity. So it is not seen in case of a long channel MOSFET, but we can observe the short channel effects in case of a very miniaturized devices having a channel length say below 100 nanometer. So these short channel effects refer to this roll-up of threshold voltage with reduced channel length, then higher value of subthreshold swing, larger drain-induced barrier lowering, then drain current when the drain current is not proportional to the reciprocal of the channel length, and the device characteristics means transfer as well as output characteristics degrade with the operation time. So here you see a cross-sectional view, a schematic view of a MOSFET. So this is the source terminal at the left hand side, and on the right hand side it is the drain terminal. These both the source and drain regions are doped with N plus impurities, and in between you will find this gate terminal, and this oxide layer is sandwiched between this gate material and this channel. So here you see that the channel length, which is at the interface between oxide and semiconductor, that is, if we denote it by L, capital L, and the channel length actually below, a few nanometers below, that is equal to L dash. So it looks like this trapezoidal shape where we find these depletion charges. So L dash is obviously less than L, and from this you can see the variation of the threshold voltage with channel length. This threshold voltage reduces as L decreases. You can see when Vd equal to Vd means the drain voltage with respect to source is 50 millivolt or 0.05 volt. It falls, it drops as L reduces. Similarly, if Vd is high, as high as 3 volt, the follow-up of VTH with the reduced L is much more prominent. So what is the reason behind it? The threshold voltage, you can define this threshold voltage as the gate voltage required to deplete the total bulk charge Q dash, QB dash in the maximum depletion rate. And VT means the threshold voltage. It can be expressed as summation of this flat band voltage plus 2 phi plus QB dash divided by COX oxide capacitance into area. So you know that the QB dash, it is the depletion charge within this trapezoidal shape of the channel, that is equal to W is the channel length, then Q is the electronic charge, then Na is the accepted doping concentration, XDT is the maximum depletion width, and then it is the half of L plus L dash. L is the channel length on the at the interface, and L dash is below it. L dash is naturally less in case of short channel devices. So therefore, you can say that for short channel devices, both L and L dash both are very small. That's why the VTH means threshold voltage reduces with decreasing length, channel length. So I think it is clear why the threshold voltage drops as we decrease or shrink the channel length. Due to this factor, this L plus L dash divided by 2. So this is actually VTH. It depends on the Q dash B, and Q dash B is proportional to L plus L dash. So L plus L dash is very small in case of a short channel device. That is why VTH it falls with decreasing L or channel length. So this is the reason why in case of short channel device, the threshold voltage falls with the diminishing channel length. So now I come to the another important parameter, that is subthreshold swing. The subthreshold swing, you know that it is the gate voltage required to increase or reduce the drain current by 1 decade. 1 decade means if we start with some value, say ID, and 1 decade above means it is 10 ID, or 1 decade below means 0.1 into ID. And the mathematical expression for this subthreshold swing, that is S equal to d of log ID divided, that is d of log VGS. It is the gate to source voltage, and whole to the power minus 1. It is actually the inverse of this quantity. So you already know that we need actually the lower value of subthreshold swing. For example, on the right hand figure, it is shown this 90 millivolt per decade, and there is a comparison with this 180 millivolt per decade. So the higher the device which exhibits a higher value of subthreshold swing is not preferred, because uh, you know that when the device is off, means Vg equal to 0, uh, there will be a considerable amount of current, drain current flowing through the device. That is called the subthreshold leakage. So that is detrimental for this low power device applications. Therefore, we prefer devices with a lower value of subthreshold swing. So for low power applications, particularly this lower value of subthreshold swing is preferred. But we cannot go beyond this ideal value, that is 60 millivolt per decade. So in case of short channel devices, we usually observe higher value of subthreshold swing. Now I come to another important uh, phenomenon, that is called drain-induced barrier lowering. So it is observed in case of the short channel devices. What does it mean actually? This continuous line actually depicts this continuous line depicts the band diagram of a MOSFET when uh, VD is the drain bias is applied. That means here first upper one, it shows the conduction band profile. It is the lower of the conduction band, and the bottom one continuous line, it shows the actually valence band in case of this long channel device, and for lower value of VD, this continuous line. But if we increase the value of VD, then this band diagram will be actually pushed in the downward direction, and that is shown with this dotted line. So, and the amount of shifting in the downward direction, that is equal to Q times VD. So if we apply a higher value of drain bias, this effect is it will shift the entire band diagram in the downward direction. You know that if we apply this positive value of VD, that means you know this electronic charge is negative, so there will be shift in energy in the downward direction. So, but if we see the source channel junction, this barrier height at the source channel junction, it is not affected, because this dotted line, it actually comes in the downward direction in between the channel, anywhere in between the channel. It does not affect the source channel barrier height in case of a long channel device. But if we consider this figure at the bottom, where the channel length is very short. So here you can easily observe that This dotted line starts from this source channel junction itself. So therefore, if we apply a higher value of drain bias, it essentially reduces the source channel barrier height, and therefore there will be a higher number of electrons that will be injected from the source into the channel. So that is why it is the barrier lowering due to the application of higher drain bias. That is why it is called drain induced barrier lowering. Drain means drain voltage. Drain voltage induced source to channel barrier height. So it is effective in case of a very short channel devices where the source comes in close proximity to the drain terminal. And you can observe this uh, effect in case of devices having channel length less than 100 nanometer. The drain DIBL can be mathematically calculated using this formula, that is VTH minus VTH means threshold voltage at higher drain bias, minus VTL means threshold voltage at lower drain bias, and this is the VDH means higher drain voltage, minus VDL means lower drain voltage. So higher drain voltage means you can apply it 1 volt. 1 volt is higher drain bias, and lower drain voltage means it is 50 millivolt or 0.05 millivolt. Sometimes we can apply also 20 millivolt for this lower drain bias. So by this way, you can also compute the value of DIBL, and you can use this unit volt per millivolt. Sometimes it is given in many papers or in many books also. So if you have any questions so far, you can ask me regarding short channel effects and explanation of how this threshold voltage is lowered in case of extremely short channel devices, then subthreshold swing and DIBL. So is it clear?
Yes.
So if you have any question, you can ask me. So Tuhin, is it clear? Then in Indrajit?
Yes, sir. Clear.
Okay. So now I come to another topic that is called the scaling. Scaling refers to downsizing of the device dimensions. Uh, it is not upscaling, it is the downscaling. So there are many advantages we get by employing this scaling. Yeah, we can improve the performance of the devices, but along with this scaling, there are some disadvantages as well. One disadvantage is I already told you, that is the short channel effects. So first you understand the impact of scaling on device performances on various device parameters. Suppose originally the device was of width W, length L. That means width is 100%, length is also 100%, oxide thickness is also 100%. If we reduce these dimensions by 30%, that is, then the new device will be of 70% of W, say it is then 70% means zero point 0.7, and length is also 70%, that means zero point 0.7. Oxide thickness, that is also 70% means zero point 0.7. So if we reduce both the lateral and vertical dimensions by 30%, so you will get a device having width equal to zero point 0.7, length equal to zero point 0.7, oxide thickness equal to zero point 0.7. So what is the area of the capacitance, means oxide capacitance? You know that oxide capacitance is WL by TO, ox. So zero point 0.7 into zero point 0.7 divided by zero point 0.7, that means zero point 0.7. So area of the capacitance will be reduced by 30%, and we will get this 70% value. So if we consider this die area means it has two dimensions, length and breadth, or width, you can say. So XY. So both the dimensions are 70%. That means zero point 0.7 and zero point 0.7. That means this is 50%. 0.49 means zero point 0.5. So you are getting enough advantages in the sense that you are reducing the die area by 50%. Means in a given area, if you can accommodate 100 devices, now it is possible to accommodate 200 devices within the same area. So who are the students of VLSI design? So you can realize the impact of this reduction in die area. Okay. So you can increase the device density by twofold. So it is a major advantage of downscaling. So now I come to the what will happen to the drain current. You know that the supply voltage VDD, it will also be reduced by 30%. That means previously it was 1 volt, now it is 0.7 volt. Threshold voltage, again it is reduced by 30%. That means it was 100%, now it is zero point 0.7. Similarly, TOX equal to zero point 0.7. So what is the impact of these parameters on the drain current? So ID, that is equal to K, W by L, mu, COX, VG minus VT, means threshold voltage whole square. So VG is decreased by 30%, as well as VT is decreased by 30%. That means if we subtract it, there will not be any change. So only change is due to oxide capacitance, that is 70%. So ID previously if it is 100%, now it has become 70%. So ID is equal to zero point 0.7. So what will happen if we calculate the delay? Delay means this COX into VDD by I1. So you know that capacitance is zero point 0.7, VDD is zero point 0.7, ion is also zero point 0.7. So ultimately you will get delay equal to zero point 0.7. So it is a great advantage you can achieve uh, by implementing this downscaling, because delay is now reduced by 30%. Therefore, the device will be faster. You can use a faster switching or high frequency operation. This new device will be suitable for high frequency operation. Now you consider power. This is the dynamic power, that is equal to C V square into operating frequency F. So you know that C is zero point 0.7, V is also zero point 0.7, and F means 1 upon delay. Delay is also zero point 0.7. So ultimately you can get power. Zero point 0.7 square means 0.49, that means zero point 0.5. So power reduces by 50%. It is another great advantage you can achieve by downscaling the device. That means power has been reduced by a factor of 2. That means you can integrate or accumulate a large number of devices within a very within some given area, so that it will not get heat up. it will not be heated because of the reduction in the power dissipation. So it is also uh, actually favors towards the VLSI to ultra large scale integration ULSI. So if you can, this is the schematic diagram, already you have seen many times. It is for the long channel devices so that you can understand the what would be the impact of downscaling. So if you have any question regarding the scaling or impact of scaling on improvement of the device performance, you can ask me. Shreyoshi, have you followed what I told you? Can you hear me, Shreyoshi, or not even listening? She is not listening. Is Kushal? Sudeep?
Yes, sir.
This joining does not ensure that whether they are present in the class or not. When I call them, they cannot respond. That means they are not in the class. So now I come to the constant field scaling. Constant field means electric field inside the device. First, Dennard in 1974, he proposed this constant field scaling. That means the field should remain constant uh, within the device. Even if you downscale the device, the field should not get increased. If there is an increase in electric field inside the device, there will be degradation of the performance of the device. That is why uh, uh, he proposed such type of constant field scaling. So how do you maintain this constant field scaling? There is some rule that you need to scale down both the vertical as well as lateral dimensions by a factor k greater than 1. Or what are the vertical dimensions you are scaling? That is gate insulator thickness, junction depth, along with the horizontal dimensions, means channel length, and you can also decrease the supply voltage by the same factor. That means the VDD or VGS, and you must increase the substrate doping concentration by the same factor K. Then it is possible to maintain the same electric field in the new device as you as the electric field in the earlier device. So in this way, you can maintain the field uh, within the device constant, and you can get the benefit of the device scaling. So that means the principle of constant field scaling lies uh, in scaling the device voltages and device dimensions, both horizontal and vertical, by the same factor k greater than 1, so that the electric field remains unchanged. The scaling actually ensures that the scaled device is not worse than the original device. So you must remember this one. In the scale device, in the miniaturized device, the electric field within the different points of the device should not be higher than the larger device or the earlier device. And in that way, you can ensure the high performance in case of miniaturized device. That means you can get benefit of the reduced delay, a reduced area, a reduced power consumption. Okay. So actually, the physics behind is that you can get the potential profile inside the device by solving this Poisson's equation. You can use two-dimensional Poisson's equation or three-dimensional Poisson's equation, particularly in case of short channel device. And if we employ this kind of transformation to this Poisson's equation, you will find that the Poisson's equation will remain invariant. And that means the potential profile, their curvature, everything will remain unaltered. Means you know that electric field that is related to the variation of potential with distance within the device. So that means E equal to minus dV dx. It will remain constant, unaltered. That means you can say that electric field will remain invariant inside the device. This is the physics behind it. Why Dennard proposed this kind of actually constant field scaling. He essentially actually made the Poisson's equation invariant under this transformation. Means reduction of all uh, vertical as well as lateral dimensions uh, by a factor of k greater than 1, and reduction of the all the voltages, supply voltages, by the same amount, and increase of the channel doping concentration by the same factor. And in doing so, it is possible to make the Poisson's equation invariant. And that means the electric field will remain unchanged in the scale device. It will be same as in the earlier device. So any question? Devapriya?
Yes, sir.
Means have you followed what I said?
Yes, sir, I'm following.
Okay.
And we need to study actually, so I'm following, sir.
Okay. So today I discussed about these short channel effects and its consequences and scalings, downscaling, and also constant field scaling. So you can also mitigate the disadvantages of short channel effects by several means. One is the halo doping. That means in the source channel junction, you can get some pockets and where you can dope it heavily so as to make the electrical channel length is equal to the so that the electrical channel length becomes almost equal to the metallurgical channel length. In that way, you can also reduce the short channel effects. You can also use some double gate material having different work functions so that you can also uh, mitigate the degrading effects of short channel effects by introducing some potential step inside the channel, in between the channel. This is another way, means double material gate, double material gate. So there are some schemes you can use this double gate MOSFET or tri-gate MOSFET. That means FinFET, so that you can increase the electrostatic field, gate electrostatic field as compared to the drain field, so that you can increase the control of gate field uh, with respect to the drain field, and in that way you can get rid of this, or at least you can suppress the short channel effects. So there are many schemes like this. Means instead of using a single gate, you can use multiple gates. That means a double gate triple gate or gate all around. Means it is some thing like this cylindrical gate. So inside the cylinder there is a channel, and then the oxide layer is wrapped on this semiconductor. Then you can this use this metallic cylinder, means hollow cylinder deposited on this oxide layer, and you can get the cylindrical type of MOSFET. And sometimes now it is very important nowadays, that is the vertical channel MOSFETs. It looks like cylinders placed on some substrate. So in such MOSFETs, there will be potential, or there is suppression of this short channel effects, or the significant suppression of the short channel effects. So there are many uh, techniques by which you can mitigate the uh, uh, disadvantages caused by these short channel effects. So I think it is enough for your first year course, this first semester course. And your examination, you can contact with your course coordinator to get the exam schedule. It has not yet been settled, but you know that in this month there will not be the examination. In the month of February, you will get the exam schedule from your respective coordinators. I have sent the reading materials today. You can go through the materials and follow my lecture. And I can give you one this home task, so that you can try to answer to this means assessment, so that you can get some idea how to write these questions. It is not that you can copy it from the notes to your answer script. It is not that, but you think how to write from reading this material supplied to you. So I can give you some set of questions shortly, and you try to answer to these questions, and you can send me through email. Okay. And
মানে স্যার আমরা
CRs
সলভ
you
করে
will
লিখে
send
পাঠাবো
me.
আপনাকে ইমেলে?
Huh?
মানে আপনাকে সলভ করে মেলে মানে কোশ্চেন অ্যান্সার গুলো লিখে পাঠাবো ইমেলে?
হ্যাঁ, ইমেলে আনসার গুলো পাঠাবে, আমি কোশ্চেন
হ্যাঁ,
গুলো 3-4 দিনের মধ্যে দিয়ে দেবো কয়েকটা কোশ্চেন। এটা আমার রিডিং মেটেরিয়াল গুলো পড়বে, পড়ে বা যে বইগুলো আছে তোমাদের কাছে অ্যাভেলেবেল থাকলে সেগুলো দেখে উত্তরগুলো তৈরি করে আমাকে পাঠিয়ে দেবে।
ওকে স্যার।
আর তোমরা অ্যাটেন্ডেন্সটা আমাকে পাঠিয়ে দিও, আর তোমাদের
আগের
কোর্সটা।
দিন অবধি পাঠিয়েছিলাম, দেখেছেন? 6 তারিখের লাস্ট ক্লাস হয়েছিল, ওটা অবধি
না,
পাঠিয়েছি।
আজকেরটা পাঠাবে।
হ্যাঁ, আজকে ওই একই সঙ্গে মানে গোটা অ্যাটেন্ডেন্স শিটটাই পাঠিয়ে দেবো আপনাকে।
না, আজকের অ্যাটেন্ডেন্সটা তার পাঠাওনি, আজকেরটা পাঠাবে।
হ্যাঁ হ্যাঁ, পাঠিয়ে দেবো।
আচ্ছা, ঠিক আছে তাহলে। All the best in the examination.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
থ্যাংক ইউ স্যার।